Thank you for the introduction. And before I start, I would like to thank all the organizers for their great work in putting together these wonderful events. It's really great to be here. As you can see, the official title of this series of mini courses is VOAs from higher dimensional quantum field theories. But that's indeed where we are going. But perhaps a more appropriate title for the first few lectures is, well, instead of talking just about VOAs, we are going to be broader, and we are going to look at quantum symmetries in general. And we're also not going to talk about higher dimensional quantum field theories for now. That's where we are going to get. So for in particular for this talk, we are going to stay very low in dimensions, like in dimension 0, 1, or 2. So here there is a word QFTs that of course stand for quantum field theories. By the way, this series of mini courses is supposed to be really elementary and pedagogical. So if there's any question or comments, so please feel free to interrupt. So quantum field theories are mysterious objects, even for physicists. And in the past, many people have tried to define them mathematically, but with a limited amount of success. In particular, for the most interesting quantum field theories, these are usually very hard to define rigorously. So instead of talking about definitions and then work from these definitions, a very useful strategy of dealing with them is that we look at various corners and various mathematical structures that quantum field theories encode. So, for example, one can, for people who are more algebraically minded, you can look at certain algebraic structures. Then you indeed can discover a lot of interesting algebraic structures. And famously, VOAs, as you have already encountered multiple times, tensor categories, and various interesting algebras. Cluster algebra, cohomological QFTs, and so on and so forth. For people who are working geometry, one can also try to hunt for interesting geometric structures. Then there are, one finds that indeed quantum field theories are gold mines for interesting geometric structures. So there are fancy things like Calabi manifolds and their moduli spaces, and interesting spaces like Higgs and Coulomb branches. And then for people interested in combinatorics or number theory, one can also try to find, look at quantum field theory from a number theoretic point of view or combinatoric point of view. But one important lesson from the previous study of quantum field theory is that these are different corners of huge subjects, and they are often very closely connected because these are different ways of looking at the same quantum field theory. So there are going to be connections between the algebraic structure that you are able to find and then geometric structures. So for this series of mini courses, we are going to focus on algebraic structures, but we are also going to keep in mind that there are various connections with geometry.
I have a slightly, if you don't mind, I have a slightly kind of maybe a little bit tangential, but I have. Sure. So I think about like the algebraic quantum field theory, like the Doppler, Haag, Roberts. I think they had this formulation. Does that fit in the picture? Do you know? I don't know if you know what I'm talking about.
So there are various approaches that can describe quantum field theory.
I guess
right. So one particular useful approach is the axiomatic approach following a T.S. style, right? So maybe let's continue with that. And then there are also various others axiomatic approaches. But maybe let's start from here, so if you don't mind.
Sounds good. Thank you.
This approach was originally designed for CFTs and then later adapted to topological quantum field theories. And then it's being also developed for other type of quantum field theories. The idea, as you have seen many times, is to view quantum field theory as a function from certain category of cobordisms. Let's say cobordism of d-1 dimensional manifolds to certain category, like category of vector spaces. And indeed, this has been a very useful point of view, especially for QFTs. But what would happen if you present this as a definition to physicists? So they will have some complaints. So first of all, in general, quantum field theories are not topological. So and it could depend on other structures here, string structures, other things. In particular, it could have metric dependence. Then that potentially will make this approach a little bit hard to work with. But that's a minor complaint, actually. The biggest complaint is probably that for most of the quantum field theories that are defined by physicists, they're actually only defined. So many interesting T's are only defined or only make sense on a space of a flat metric. Let's say R to the D, or potentially R D minus 1, 1, with flat or Euclidean or Minkowski metric. So then it's hard to use this kind of approach. But then one can, instead of considering cobordisms, one can look at operators, which is needed if you want to really make this an extended TQFT to start with, right? So then, in principle, one can still apply a certain axiomatic approach by looking at all possible operators and then how they, the algebraic structure, presumably some higher category that they form. But that's also kind of difficult because many interesting quantum field theories come from quantizing classical theories. That's potentially a third complaint for physicists. So this approach, so it's not very useful to describe the so-called Lagrangian theories. So what's the meaning of Lagrangian theory? So we know that in classical physics, in classical mechanics, there are different approaches. One particular approach is that you start with an action and then apply a certain variational method. And that approach is easily quantizable. But the theory that one obtains, it's very hard to look at the collection of all operators and how they interact with each other. So that's potentially another complaint for physicists. So what we will do now is that we will start very low in dimensions, and then well, because I assume that it's not true that everybody has some previous exposure to quantum field theory, so I will first start in 0 dimensions, and then gradually work our way up until we are getting more interesting dimension like 2D, 3D, 4D, and potentially 6 dimensions. So, but before that, is there any questions? So what is a 0-dimensional quantum field theory? Atelier and Siegel would tell us that we should look at cobordism of -1 dimensional manifolds. That's slightly ill-defined, but what we can do is to ask what's the partition function, or what's the number it assigned to a point. this is what one would refer to as the partition function of the quantum field theory. So actually in zero dimension, this approach is very simple. That's all there is. So you just have this partition function. And then if you consider having 2 points, distant union of 2 points, then one of the axioms would tell you that it will be just square of this. That's basically the end of the story. But then physicists would tell you that, well, how about Lagrangian theories? Then it's a great opportunity to introduce the notion of path integral and also fields in the language of path integral. Let's consider a particular field known as real scalar field. So before, it's supposed to be a real valued function on your spacetime, but now the spacetime is just a point. So it's just a variable. It's a map from a point to R. So it's just a variable. And then in the path integral, you are supposed to integrate over all such maps. But now that just corresponds to integrating over all possible values of x from, let's say, minus infinity to infinity. And then the integrand is something that is controlled by function. In general, it's a functional, but now it's just a function of x. It's also known as the action. And then this, in the path integral formalism, would just be the partition function for what this quantum field theory associated to the point. So this action can be complicated or it can be really simple. So let's check out some examples. Example number 1. So S is alpha over 2 times x squared. This is really a very simple action. It's just x squared. And then what happened to this integral? Well, it becomes a Gaussian integral. And this is why this theory is also sometimes referred to as Gaussian theory. Some people will use the word, the term free theory, because this is indeed the analog of free theory in zero dimension. So one manifestation that is free is that the integral is really simple. So in this case, d would equal to something like 2 pi over alpha, square root of that, if I have it correctly. Then, in the path integral formalism, partition function is not the only thing that we are interested in. We also have correlation functions. So here, f is just some function of x when considered in general real valued or complex valued. And this is defined as the same integral, but with this function f inserted. So again, in this example, it's going to be relatively easy to compute this kind of correlation function. If you are able to, if this is a polynomial, then you know how to deal with it. If it's not, maybe you expand that in series. Example number 2, if I still have this, and then I have something else, I times epsilon, x cubed. So what should I do? So now I don't know how to do this integral in general, but I can work order by order. So for example, I can work with, well, for the first order, it's going to be 0, but for epsilon square, it's going to be non-zero, and it's going to be given by something like x cubed times x cubed exponential of minus alpha over 2 x squared. with some coefficients. So physicists look at this kind of problem, and they manage to develop entire machinery known as Feynman calculus. So we'll start with certain diagrammatic tools known as Feynman diagrams, and then assign a certain numerical value to the Feynman diagrams. So for this particular example, for some reason, the two diagrams are going to be this one and this one. So as you might have guessed, there are two vertices because they are 2x cubed. And then somehow they have to be contracted in the proper way so that it can contribute to this integral. So I will not go into detail of this. This is just to mention that already here, there are some interesting combinatorics going on. Any questions at this point? So, yes?
Can you explain how you got the integral for epsilon square?
Oh, so here we're just expanding. So we're just expanding this exponential of minus alpha over 2 x cubed minus I epsilon x cubed, right? I'm just expanding this as integral of dx e to minus alpha over 2 x squared, and then with a sum, right, over n from 0 to infinity, I epsilon minus I epsilon to the n, and factorial, well, x cubed, right?
Yeah, thanks.
And then if I want to get the correction proportional to square of epsilon, this is a kind of integral that I will have to do. So any other question?
And on the other term, it gets vanished because x cubed is an odd function.
Yeah, that's right. Any other question? So because I promised some connection with geometry, so let's even in 0 dimension mention a model where a manifold is used as the input. So this is the example of a sigma model. So what's the meaning of this? So before, this x is a real variable. Now I want this R to be replaced with a manifold. So x is now the map from the space-time, which is a point, to manifolds. Let's say some n-dimensional manifold, mn. Then my integral will not be just integral over the real line. It will be integral over this manifold. We need to specify certain measure, but we will have an integral. And then instead of computing this integral, giving the correlation functions, we are computing some integral of some functions over this manifold. So that's a sigma model. So we can even make this more interesting by adding fermions, which are models of various differential forms here. So you know that one forms are supposed to anti-commute, and they behave somewhat like fermions. So there is a certain trick of adding fermions to the path integral. And with that, you can, instead of just getting integral functions, you can get integral of differential forms. So I will not go into this description at this moment, unless you really want to learn about it. That's probably all of the 0-dimensional story that I want to bother you with. So we are now going to move to one dimensions. So what is one-dimensional quantum field theory? Again, we can work with a path integral. Feynman would probably do that in that way. But alternatively, we can view this as quantum mechanics. What's the meaning of this? So what is quantum mechanics? So quantum mechanics is about studying the evolution, time evolution of quantum systems. So at this particular time, t equal to 0, we will have a Hilbert space. So this is going to be a Hilbert space of quantum states of the system. Indeed, that's if you look at the axioms in the Atelier style, that's exactly what you are supposed to get. So for 1D theory, and then for zero-dimensional thing, you are supposed to have a Hilbert space. So here, this is consistent. And in quantum mechanics, we are supposed to study the time evolution of this. And then there's also going to be an algebra of quantum operators acting on a Hilbert space. That's, well, a familiar setup for quantum mechanics. And then inside this algebra, there is supposed to be a very special operator known as the Hamiltonian, which is a Hermitian operator that controls the time evolution. So you can regard this as the axiom of quantum mechanics. So indeed, if you have gone through quantum mechanics classes in undergrad, this is the basic assumption that you have been working with. Alternatively, you can view this as a consequence of this axiom. So these are compatible. So at time t equals 0, you have a Hilbert space. At a future time, t equals to let's say t0. You are supposed to have another Hilbert space that is isomorphic to the previous one. But then quantum mechanics will tell you that there's going to be a map that tell you the evolution of state. So we have h t equals 0 map to, sorry, this is this h Hilbert space equals to t 0. Sorry about the slightly confusing notation. And then the evolution of a particular vector here is supposed to be given by e to minus I t0, then the Hamiltonian, then over parameter known as Planck's constant. So why do we need Planck's constant here? Well, historically, it's certainly needed because we work, so time has certain units, right? Second, millisecond, so on and so forth. Hamiltonian is associated with the energy, also has certain units. And then if you multiply time and then energy together, somehow it's hard to make sense of this as a number. So Planck constant is needed, even just from that kind of perspective. So therefore, if you really defining certain quantum mechanics that come from some classical system, you have this parameter, and everything is going to be labeled or depend on this h bar. So in particular, this A will be labeled by this parameter h bar. And then you can send this h bar to 0. In that limit, you are supposed to have something that is commutative. So h bar equals 0 is supposed to be a commutative. commutative algebra. And then from that algebra, you should be able to recover the classical mechanics. There should be some certain phase space that is a Poisson manifold, and then you are able to do classical mechanics there. So if your quantum mechanics does not come from a classical system, in principle, you will not need this. So there might not be one parameter family whose limit is some commutative algebra. So we will later quickly forget about H bar. So this is the Hilbert space. How about the partition function? So if you think about the axioms, it's kind of obvious what the partition function should be. So first of all, the non-trivial one manifolds are circles. And because we're working with quantum field theory that may or may not be topological, this will have certain sides. I'll just use T0 again to denote the sides. And then if you think about it, this number had better be a trace of exponential of minus I T0 times the Hamiltonian H. So that's the partition function. So what's the interesting algebraic structure here? Not much, unless you just come up with a system with an interesting algebra of operators, right? So the only canonical operator here is just H. H is a Hermitian operator, so there's some spectrum. The eigenvalues are known as energies. So there can be some states with energy eigenvalue equal to 0. And then there can be some states with energy eigenvalue being non-zero. But one can make this slightly more interesting by adding supersymmetry.
If I remember well, Z was defined as a functor from cobordisms to vector space.
Yes.
So I think I don't understand the notation trace H of exponential minus I T0 H. Is it supposed to be a vector space?
Oh, so here, this is supposed to be an operator that acts on this vector space H.
Yes.
Right. And then we can talk about the trace of this operator.
What is the trace? It's okay, but so my question is,
so it's just going to be a number.
Z was defined to be a maybe what's something wrong, but I thought Z was supposed to be a functor.
Right. So Z is supposed to be a functor. When it applied to a closed D manifold, here D equals 1, we're supposed to get a number.
A number?
So it takes the boundary of vector space. All this between boundaries.
It's,
right.
Yeah, because okay. No, in fact, I know that.
Okay. So for points,
Yes.
the functor would assign that to vector spaces.
Okay.
Right. And then to intervals like this, the functor is going to assign a map between this vector space and this vector space.
And the vector space are one-dimensional in this case?
No, so the vector spaces are, this Hilbert space is 0 and H1.
Okay.
So they are not necessarily one-dimensional. They could be, but here in this picture, I have assumed that it's high-dimensional and have a lot of eigenstates for the action of the Hamiltonian.
Mm-hmm.
So this for this you have a map. Okay, and then what happens for the circle?
They have the same thing.
Yeah, they're supposed to be isomorphic.
Yes.
Right. So and then right, and then this map is actually this map over here, given by exponential of minus I t times the Hamiltonian. And then how about closing this up now? Then I'm going to have a trace of this operator.
Okay.
Is this clear? And yes.
Yes, I have a question. Are we assuming that H is finite dimensional?
So we are not at this moment. So then it's important that for well-defined quantum mechanics, actually, this is of trace class.
Cool. Thank you.
But well, I could imagine that there can be useful quantum mechanics that go slightly beyond this, but we will stay in this framework that this trace is always well defined.
Thank you.
So, any other question?
No, just like this.
Yeah. So, if we just have this Hamiltonian, then thing is slightly boring. But we are going to introduce supersymmetry. So. This is actually n equals 2 supersymmetry. You will soon see why it's called n equals 2. So recall that because we are working with quantum field theory in d dimensions, and if you consider just the Minkowski metric, then this is acted upon by an isometry group, and then they're going to be operators coming from this way. Considering supersymmetry means that we are going to instead of just looking at isometry of Dn, we're going to assume that we can consider certain super space. So more concretely, in this case, what we mean is that we just consider finding a square root of the Hamiltonian. So we introduce operator Q that has a property that the anti-commutator of Q and Q dagger defined to be Q dagger plus Q dagger Q. This equals to 2H. And then square of Q and square of Q dagger are going to be 0. So that's the supersymmetry algebra for super quantum mechanics. So here, n equals to 2 basically means that Q and Q dagger are not the same. So if you want to get to n equals 1, you just take the sub-algebra generated by QR, which is Q plus Q dagger. So for this algebra, it's usually assumed that we also add another operator that has a property that the commutator with F with Q is given by Q, and the commutator with Q dagger is minus Q dagger. And F would commute with H. For the n equals 1 quantum mechanics, F would not make sense, but one can still have a well-defined F mod 2, it's minus 1 to the F. This can be well-defined. So this is going to be the n equals 2 supersymmetry algebra. This is going to be the n equals 1 supersymmetry algebra. And what can we do with this? And what kind of physical theory could have this supersymmetry? Is there any question? Yes.
What is F?
It's just an operator. So we will just refer to this as fermion number, because, well, Qs are fermionic. At least that's the expectation. And then it's charged non-trivially under F. So if you have something that does not have fermion number, and then you ask by Q, that would have a fermion number. So this is how this works. And when if the fermion number is even, we would refer to an operator or state as bosonic. And if this is odd, we will say that this operator or state is fermionic. Then, as you can see, H is bosonic, has a 0 fermion number. Q dagger and Q have fermion number plus or minus 1, and they are fermionic.
Does
Yes.
equals H?
Yeah, so it actually follows from this that Q and Q dagger, they both commute with H. Yeah.
Okay, representation of J11.
Representation of, sorry, what? Yeah, it's supposed to be. I think so. Yeah, so this is very simple algebra, right? So then, if a theory have this kind of action of this quantum symmetry, what would happen? So something might happen to this picture, right? So first of all, before, there's no reason for the spectrum to be bounded from below. Yes.
Can H be interacting? Or is it just a free?
So here H is just an operator on the Hilbert space, right? So in some cases, you can switch to a different picture and say that it's a freely Hamiltonian.
Yeah, like
But in general, it's interacting thing, right? So yeah, so in some picture, maybe H, vectors in H are represented by wave functions. And then this Hamiltonian is represented by some operator, right? Differential operator. And then there's a clear notion of being free and not free. But in general, we're not able to say that well, it's interacting or free, right? It's just some abstract operator acting on this space. Yeah. It's assumed to be generic. Any other question? Right. So before it's not even clear whether this spectrum of for H is bounded from below. But actually now, because it's a square, one can show that for any eigenvalue, so I will use this fancy notation for vector in the Hilbert. So E has to be non-negative. So then there are two different cases, either E equals to 0 or E not equal to 0. And they are actually going to be quite different. So if I have a state that has non-zero energy, so here the word energy is referring to the eigen value of H, right? So maybe I will write it energy. Then we can X by Q or Q dagger. We can get something. Then, if we X by Q again, we're supposed to get 0 because basically Q squared has to be 0. And then if we add Q dagger, we're going to get back. So that's a particular representation that we can have.
I'm sorry, what are the orange circles representing here?
So here, these are just two states.
Okay, thank you.
Yeah. So and then if this is a Bosonic state, meaning it has even F number, then this has to be a Fermionic state. So this will be a class of representation. Another class will simply have the parity of these two switched. I have a Fermionic state, and then on the other side, a Bosonic state. So, and then if you think about it, these are the only finite dimensional representations that you can ever have for this algebra. One is non-zero. So what happens when E equals 0? So if you start with now, because H, the action of H will be 0. And then if you think about it, you can only have these two representations. Either you just have a single Bosonic state or a single Fermionic state. So these are this is representation theory for this algebra. Very simple, right? Now, what's the benefit of having supersymmetry? Supersymmetry, having supersymmetry means that certain quantities in the field theory become quite robust. So what's the meaning of that? If you look at that partition function, it's not very robust. If you change H a little bit, or if you change the size of the circle a little bit, you have a different number. But here, what you can do is to define something that is an invariant of the supersymmetric quantum mechanics. I just define it as, well, the name is Witten index, and is defined as the number of bosons or bosonic states minus the number of fermions. So what's special about this quantity? So if I'm looking at higher energy states, they will never contribute to this index because boson and fermions have to come in pairs. So only zero energy state can contribute. So this would also equal to the number of bosonic zero energy states or bosonic zero modes. So zero modes is just a different name for zero energy states minus the number of fermionic zero modes. So then this become something that is simpler to compute, right? And this has to be an integer. And because it's an integer, in general, you expect that under a lot of deformation, it's supposed to be invariant. It's hard for integers to change continuously. And from the point of view of the spectrum, this is also kind of obvious because for higher energy states, you always have the same number of boson and fermions. And then at the ground state, there can be different number of boson and fermions. You can have 2 bosons with 1 fermions. And then imagine that you deform your Hamiltonian or the quantum mechanics such that some states from higher energy come down to ground state, and some of ground state leave to be excited. But because everything that enter or leave the ground state have to enter or leave in pairs, this number will not change. So this is supposed to be an invariant in that sense. Of course, there's well, in physics, there are always caveats. Oh, yeah, is there a question? Right. One caveat here is that here there are still some assumptions. We're assuming that we are dealing with very good quantum mechanics. So what could go wrong is that there can be a continuous spectrum, and then there can be some infinite dimensional spaces happening at some point. So those would lead to an interesting phenomenon known as wall crossing. So you might have heard about the term wall crossing in different kind of contexts. So almost all of them can be we can trade the origin into the world of quantum mechanics. So right, so this is kind of a robust invariant, but sometimes it can also jump. What is this number from the point of view of axioms for quantum mechanics? It's actually something very simple. So you have again the quantum field theory functor. You can still consider the partition function as one, but because we are dealing with this theory with fermions, we also need to choose the spin structure. And here, this is a particular spin structure that I will denote by P. P is for periodic, meaning that it's periodic boundary condition for the fermions. And from the point of view of spin cobordisms, it's a generator of spin cobordism in 1D. So it's the non-bounding spin structure. So on S1, there are 2 spin structures. One is compatible with being a boundary of a disk. Another one cannot be bounded by a disk. And we are talking about that one. And because we are having this particular boundary condition for the fermions, then the the way to write it in terms of operator is going to be slightly different. It's still trace of certain operator acting on H, but it will be -1 to the F times e to minus I T0 H. Well, I will forget about the Planck constant. So here, it seems that it still depends on the size of the circle. But actually will not, because again, the states with higher energy, they will not contribute. In the end, if you just look at it, you will be given by exactly this expression. Because for this trace, you can decompose this as a sum over the eigenstate. Then you will see that higher energy states will cancel. This is this quantity in the language of QFT axioms. So here, it's clear that this is counting something. So maybe we should try to categorify it. So instead of using this as an invariant, we can just talk about this subspace of ground state, right? And this can be decomposed according to the eigenvalue for F. And this actually has a different interpretation. This can be interpreted as the Q cohomology. It's an operator that squares to 0. So then we can talk about the cohomology of Q. And if you think about it, you will be exactly this number, well, this space. So this is not just a fancy mathematical trick that we are doing. So there's actually some physics going on. So this Q cohomology can be naturally identified with the Hilbert space of the twisted theory. So here, twisted is in the sense of topological twist. So I maybe should better say the topologically twisted theory. So what's the meaning of that? So I have a Hilbert space, and then I have a Q, and then I can look at the action of instead of the action of the entire algebra, I look at the action of Q closed operators. And then I can just work with Q cohomology. And then I have a slightly different quantum mechanics. I have algebra acting on a Hilbert space, that's quantum mechanics. The time evolution now is just trivial. So the Hamiltonian twisted equals 0. This is a topological theory because there's no time evolution. So the metric on my manifold will not matter. So this is a procedure known as topological twist that later will play interesting roles. But here, this is just something very boring. This is just about passing to Q cohomology from the Hilbert space. Okay, so what is an example of quantum mechanics in real life or in, I don't know, math that could have this supersymmetry? It's not hard to get one. In fact, it's going to be a sigma model. But now it will not be a zero-dimensional sigma model. It's a 1D sigma model, or equivalently, sigma model as supersymmetric quantum mechanics. So the Hilbert space will now be differential forms on your manifold. Let's say complex value. And then Q would become the differential D. Q dagger will be D dagger. To define it, you would either need a metric or maybe a way to define the hot star. And then what is the Hamiltonian? This is 1/2 Q dagger plus Q dagger Q. This is Laplacian, right? And what are these spaces? So H0 would be, well, zero energy space means the space of harmonic forms. And then indeed, from Hodge theory, we know that this is the same as Duran cohomology, which is indeed Q cohomology. So, which is the Hilbert space of the topologically twisted theory. So this is simple quantum mechanics, and then you see that there's some geometry going on already.
So
Then,
could be arbitrary.
right. So M is just an arbitrary manifold. So, and then you can use that as an input, and then you can define this quantum mechanics, right? So given some state here, I know how to evolve it, and so on and so forth. So that's the quantum mechanics. So the last thing that I'm going to mention in 1D is that, well, here, what is the partition function? If you think about it, this is simply the Euler characteristic of M. That's indeed dimension of even degree components minus the dimension of the odd degree components. And F is just a form degree. So F number or fermion number is just the degree of the differential form. So now we are going to move to 2 dimensions, but before that, any question? Yes.
What's the categorical interpretation of the operator mathematics?
The categorical interpretation of the half. Sorry, of F. So here, F, the eigenvalue of F is this fermion number. So it's just this degree over here. So if I'm given a form, it can be an eigenstate for F, meaning that I have a definite degree. And then that's just the form degree. Okay. Any other question? Okay, so we are.
For this cohomology ring, I could also assign just this alternating sum, but I could assign Q power series where there's only dimension. Right, so Q to the n dimension of the n cohomology, is that empirical relevant?
So in this case, yeah, so it's possible to, so there are ways of interpreting it. It's not actually a supersymmetric partition function anymore. So this is a supersymmetric partition function, but the Poincare polynomial, you can interpret it as now you have, so you have this F, that's a symmetry, right? And then actually part of the axiom that one should have is that now I can turn on a holonomy for certain background of this symmetry. So turn on some background connection A for this F. So that's something that is possible, but this will in general break supersymmetry. So it will not lead to a very nice partition function. And that's why a Poincare polynomial is not as invariant as the Euler characteristic.
Yes, I just want to see if I understand. So the Euler characteristic is the Betty number for like, if you will, at 0, 0.
The Euler characteristic is the
Like,
B even minus B odd, right?
yeah, so which is like Q of the 0 state minus Q dagger of the 0 state.
So it's a number of even harmonic forms minus all harmonic form, or in that language, number of bosonic zero mode minus number of fermionic zero modes. Is this clear?
Yeah, yeah.
So am I allowed to move to 2 dimensions? Okay, so in 2 dimensions, we will have now action of isometry group of R2 or R1, 1. So then there is going to be a time translation. We're still going to say that it's generated by the Hamiltonian H. Then there's also a translation in the space direction. So it's customary to use P in physics and denote and say that this is an operator corresponding to momentum. So it's a momentum operator. And then there's also going to be either a rotation from the Euclidean point of view or Lorentz boost from the Lorentzian point of view. There's an operator M that generates that. And the representation theory of this is also a little bit boring. So, but can we make it supersymmetric again? No, because if we want a square root of H or P, we are going to have spinors. And spinor in 2 dimensions can be either left moving or right moving. So we are actually going to have 2 types of spinors. So we can have certain Q that are, well, I would say that this is right moving. And then they'll have the property that Q square of this equals to basically H minus P. And then there can be left moving supercharges. And Q minus square would be H plus P. So there can be 2 different types of supercharges. And then we have different amounts of those as well. So in 1D, we use the notation n equals 1, n equals 2. So here we cannot use that anymore, but instead we will say that n equals to n left, comma, n right, because there can be different numbers of those. So what's the minimum number of supersymmetry? The absolute minimal is 0, 1. Or 1, 0, but we just work with 0, 1. That means that there is a single Q plus, and then square of that Q plus is H minus P. So that's a particular class of theory that will play some interesting role tomorrow. Then we can have non-minimal. But we can ask, what is the smallest possible amount of supersymmetry such that we can perform topological trees? And the topological trees, the answer turns out to be 0, 2. So when it's 0, 2, there are going to be 2 Qs, and you can form this combination. You can complexify them and consider Q bar and Q. So these are, I'm now using complex notation. And then instead of having square of them being H minus P, they will square to 0. But instead, their anti-commutator would be proportional to H minus P. So maybe this is slightly confusing because here, this is not really a compact notation in contrast with this guy. So I hope this is not too confusing.
So this Q plus will now be somehow Q plus 1 plus I Q plus
yeah, exactly. Yeah. Yeah, exactly. So it's an interesting exercise to just do this. Q plus 1 plus Q I, Q plus 2, and check that indeed they satisfy this relation. So then for this, we can perform topological trees. What's the meaning of that? It means that there is going to be Q plus cohomology. And for a reason that I'm going to explain later, Q plus cohomology, that would have a structure of VOA. although the theory that we are starting with may not be conformal. So we are talking about general theories. So there are no conformal generators here. But nonetheless, we expect that the Q cohomology to have a structure of a VOA. So one can have even more supersymmetry. So another case where we can have other interesting topological twists is when we have 2,2 supersymmetry. So 2,2 means that we are now having Q minus bar, and then also plus. So there are going to be 4 supercharges. And again, using this complex combination. And then there are going to be now some new combination of the Qs that square to 0. So there's going to be QA and QB. So let me make sure I get the Q plus bar plus Q minus. And this is, so these are some combinations that also are nilpotent, namely the square to 0. And then they can be used to define, again, Q cohomology and topological twist. So if you use this is known as the A twist. So you will get something that is known as the A model. If you do this, you will have a B twist and get something known as a B model. And then there is a story that presumably some of you are familiar with, that there is certain automorphism of the theory that exchange these two. And that's playing some interesting role in mirror symmetry. So there's some A model and being mapped to a B model, and the KVL is replaced with a mirror. So that's an interesting story by itself, but we're not going to focus on that today. So if we perform topological twists, the theory will actually become topological. So, so for these cases, we should actually get 2D QFTs. So we will talk a bit more about this maybe on Wednesday. But for the remainder of today and tomorrow, we're actually going to talk about this case. I mentioned that for 0,2, this is a way to get some VOA, but why we are now working with 0,1? Can we get interesting statements about VOAs if we look at this particular class of theories? So one reason to focus on this class of theory is that it's the most general. It has the least amount of supersymmetry. So if you have any supersymmetric 2D theory, it must have a 0,1 supersymmetry. So it's the most general. And then there are some interesting statements that one can make about it. So, but for the remainder of this lecture, we are just going to set up some stage, and then we are going to explore the interesting world of 0,1 theories. So, one operation that acts on quantum field theory is something known as the RG flow. RG is for renormalization group. What is this about? So we are having some theory, let's say R to the D, and then isometry of R to the D will act on the theory. We're going to be symmetry of the theory, but then one consider scaling of this space. We can scale it, and then we'll get a slightly different theory. So the picture is that if we start with a theory, and then if we perform this action, let's say we zoom out, then we are going to a flow. If we are zooming out, we will say that we are flowing in the infrared direction. We'll have trajectory of different theories. And then in a limit, one can, in principle, have another theory, T, IR for the infrared. that serve as a fixed point of this flow. What's the meaning of being a fixed point? Being a fixed point means that it's a scale invariant. So this is supposed to be a scale invariant theory. And in 2 dimensions, it's actually well proved by physicists that this is the same as being conformal. So if we have some theory, and then even if it's not scale invariant, we can flow in some way and get a conformal field theory. So that's a way of having something non-trivial to say about VOA by working with general 0,2 theory. So we have 2D theory, and according to the axiom of quantum field theory on S1, the functor should give us a Hilbert space, right? So I will just denote this by H S1. And then it's easy to see that this Q plus will generate an n equals 1 supersymmetry algebra in the 1-dimensional sense. So I have unfortunately erased it, but recall that there's a way of having an n equals 1 supersymmetry algebra acting on Hilbert space. So here, this Q plus will exactly generate such an algebra. And as a consequence, one can again define this kind of Witten index. One can actually do it, define something that is even stronger. So this is because on this Hilbert space, there's another action. There's the U1 action coming from the rotation of the S1. Therefore, one can decompose this into different pieces. And then the same is actually on each component, you have an action of this algebra. In other words, this U1 action commute with the action of Q. So now what happens is that you can define a Witten index for each of this. And then you can actually sum this over with a Q. So then you will have, you can define, I will write ZQ for now. So this is Q to the N, and then times the Witten index of the N's components. So, what do we know about this quantity? So in principle, it can be a formal series that may not even truncate in other directions, right? And so as we will see next time, this is actually going to be a very nice quantity. It will have some modular behavior, and it will, in some cases, be identified with VOA characters. And then we're actually going to use some statement about 2D 0,1 world to tell whether whether some of the QS can or cannot be realized. So that would put some constraints on what kind of Q series can be VOA characters. So that will be our job next time. So let me end it for today.
Thank you very much. Do we have some more questions?
So in the final example, do you consider 2D QFT or CFT start from?
So in this example,
yeah,
it's about a general 2D 0,1 quantum field theory.
QFT.
Right. So here, I'm just talking about the action of supersymmetry algebra that comes from the Q. So I'm not using conformal symmetry in any way.
I see.
Yeah, but as we will see later, so this, well, it's again an invariant. And in particular, it's going to be invariant under the flow. So then this will lead to some prediction about the conformal theory and also some statement about the VOA characters.
Thank you.
So I noticed you're sticking quite strictly to Hilbert spaces in your formulation. So you're using the positive definiteness of the scalar product. So obviously there are many examples in conformal field theory where we drop that requirement. What changes? How I mean, can we incorporate that nicely into this theory, or do we have to?
Yeah, that's actually a great question. So for the thing that I'm going to say next time, I actually don't know the answer. So the statement that I'm going to make next time will apply to unitary theories, which means that there's certain inner products that deposit definite. But I would suspect that it would also hold for non-unitary theories. So tomorrow you will maybe if you would tell me whether that prediction is could be correct for non-unitary theories as well or not.
Maybe comment on that. In my opinion, the space here, their perspective space, we do not really use very much the scalar product concept. In physical applications, there are state spaces of physical distance, and then you typically want that property. But the spaces we have in conformal theory are spaces of conformal block, for example.
Yeah, I think for many applications, this assumption is not needed. So tomorrow I'm going to mention some statement about the space of theories. And that seems to be a space of unitary theories, but I would suspect that maybe adding non-unitary theory will not change the homotopy type of the space. But well, you will tell me tomorrow.
So in this last example, the HN is the N cohomotopy.
Oh, so here I'm just decomposing with the U1 action.
Yeah, and then the HN is the U1 eigenspaces.
Yeah, exactly. Yeah, so tomorrow I'll say more about this quantity and from a different point of view. So it will be should be clearer.
But then let's thank you again.